Okay, let's move on to the third and fourth pages um, in the handout for tonight. And what we're going to be doing is talking about elementary row operations, um, reduced row echelon form, and row echelon form. I'm going to talk about the possibilities for the number of solutions, and then I'm going to show you how to solve systems by using back substitution. Um, After this, I am actually going to insert a little bit. I'm going to show you how to use MATLAB or Octave or your calculator to do some of this grunt work, because this is a fair amount of effort to reduce these matrices. Okay, the elementary row operations, these are actually the things that we have been using to row reduce a matrix. So we just want to formalize them now. What are the legal operations? Well, you could multiply a row by a non-zero constant. You could interchange the locations of two rows, or you could add a multiple of one row to another row. And those are the only things you can do in order to row reduce matrices. And the point of limiting the options to these is, first of all, we have a systematic way of transforming from one matrix to another. And if we follow these rules, we're guaranteed not to change the solution set. So the solution of the final system that we generate will be the same as the solution to the original one, and that means we've solved the original problem that we're working on. Now, when we are trying to row reduce matrices, what we've seen so far anyways, we're trying to get it into the reduced row echelon form. And we use this term so frequently in this course. We just say RREF, and it turns out that that's what our calculators and MATLAB say too. So that's a great abbreviation to remember. So now, row reduced echelon form, I'm going to go over these rules, but let me just take some examples here and show you before we dive into the rules. What they say is this: if you pick any row in a reduced matrix, you're going to find a couple of different patterns. The first one is this: as you scan across the row, the first non-zero entry that you encounter has to be a 1. So I scan across this one, first non-zero is 1, first non-zero is a 1, that one passes that first test. As a matter of fact, all of these pass that first test. If you scan across here, first non-zero is a 1, first non-zero is a 1, same all the way down through there. Now, it does not mean, however, that we're always going to get 1s down the diagonal and 0s above and below, because you'll notice in this case, well, that's not quite reduced. That would need to have a 1 there. You can get it by dividing this by 2. So that is this first rule here in reduced row echelon form. The leftmost non-zero entry of each row is a 1. These are called leading ones. All the entries above and below a leading one are zeros. Now that's if you're in RREF. So everything below the leading one is a 0, everything above and below is a 0, everything, of course there's nothing below, right? But everything above and below is a 0. This one passes the second test. This one, by the way, does not pass the second test. Everything below a leading one is 0. That actually is true all the way through this matrix, but the things above the leading ones are not guaranteed to be 0. So this is not RREF, and that one's not RREF, but this one is. So we can mark that. That's a reduced row echelon form. This is not. There's another form that these are. This one is not because of this right here. It's not either of the two forms we're going to look at. And this one turns out to be RREF. Now, you might think, whoa, wait a minute. There's a whole bunch of garbage in there. That's true, but I've only got two non-zero rows, right? And the first non-zero entry is a 1. Anything above or below a leading 1 is a 0, and it passes the other test that goes along with this. Now, the next is this: giving any two leading ones, the one occurring further to the left must be above the one occurring further to the right. So it's all it's saying is this: as you look at these leading ones, as you go further down, they move further into the right in the matrix. So I don't have something like a 1 here and then a 1 here. That's not allowed. So, and it's very easy if the matrix passes every other test, it's easy to fix that. You just swap around their order. So the leading ones sort of cascade down and to the right, and it is possible that they could skip. For instance, this thing might all go to 0, so it wouldn't always be one step, but it is always true that if you look at two leading ones, let's compare this one and this one, the one that's further down is further to the right. Or to say it in the reverse way, the one that's further to the left has to be further up. Okay, we're almost there. What's row reduced echelon form? Leftmost non-zero entry is a 1. All the entries above and below leading ones are zeros. Given any two leading ones, the one further to the left must be above the one further to the right. And finally, rows containing only zeros are grouped together at the bottom of the matrix. And you see that happening right here, right? We got 3 of the 5 rows are all zeros. That's fine because they're grouped together at the bottom of the matrix. Now, if you obey all 4 of those rules, then you have an example of a matrix that's in row-reduced echelon form. If you modify this rule right here just a little bit, it says all entries above and below leading ones are zeros. Well, how about if we relax that a little bit? All entries below, but not necessarily above. All entries below a leading one are zeros. Then you have what's known as the REF, or row echelon form. So this one that has garbage above those leading ones, this is an example of row echelon form. This one, this is neither, because it has a leading 2 rather than a leading 1. This one is row reduced echelon form. This one, it's got a non-zero above a leading 1, so this is row echelon form. And this one right here is reduced row echelon form. We have all 3 possibilities: reduced row echelon form, and neither one occurring here. Okay, now when we solve a system of linear equations, I already mentioned this, but let me just highlight it because it's in the notes here. Only 3 things could happen. There's one and only one solution to the system, in other words, a unique solution. There could be infinitely many solutions, or there could be no solutions at all. So what we're saying, for instance, is this sort of thing could not ever happen. You couldn't have 4 different solutions, but not 5 of them. As a matter of fact, if you have 2 different solutions, you're guaranteed to have infinitely many. There is some vocabulary that's worth reading here. If a system has no solution, it's called inconsistent or overdetermined. By the way, inconsistent and overdetermined mean the same thing. They're not 2 varieties of no solution. They're synonyms. If a system has infinitely many solutions, we say it's underdetermined. It is consistent because it has a solution. It's underdetermined because the solution isn't unique. And a system with only one solution, well, it's consistent, it has a solution, and some people call that completely determined. It's not really that common, but I've seen it. And you could also simply say it has a unique solution. Okay, now I would like to talk about how to read solutions from matrices. Let me see, we kind of did that already on the previous pages, so maybe I won't say much more about that, but what I haven't talked about so far is back substitution. So let me give you an example of back substitution. And then I want to sneak in a little bit of talk about how to get some help from your calculator or your computer to do some of these row reductions. I am going to take a look at this guy right here because it's pretty small. This one is in row echelon form, and when we're doing back substitution, that's what we are working toward. We reduce to the row echelon form, and then we perform what is known as back substitution, and you'll see what that means in just a moment here. So I'm also going to change notation here a little bit because it's time to kind of do this in the more mature way. In high school, of course, it works to do like X and Y and Z or whatever. But if you think about it, in real world applications, you could have thousands or maybe even millions of variables. And you only got 26 letters, right? And furthermore, you'd like to have some letters left over to represent other things in your system, in your work. So usually what people do in linear algebra is the first one they call, the first variable they call x1, the second one x2, third one x3, etc. So I'm going to be writing that way really for the rest of the course now. So this one says x1 minus 2x2 plus 0, you could say 0x3 if you wanted, equals 3. This one says x2 minus x3 is equal to 2. And this one says x3 is equal to 0. Now, it's a perfectly good way to write it. There's nothing wrong with that at all. But what I want to do is say x1 equals, push everything else to the other side of the equation. And I'll list the constant first, like we did when we were preparing to write vector forms. So x1 equals 3 plus 2x2. And just for completeness, I'll say 0x3. But of course, you know, once we're used to this, we wouldn't bother. x2 is 2 plus, I'll put the x3 here just to line them up. And then finally, x3 is equal to 0. All right, now here's the point of back substitution. We actually have completely solved for the last variable, x3. That number can be plugged in here. And then that tells me that x2 is equal to 2 plus 0, which is 2. And now I know the value of x3 and the value of, whoops, I made a mistake here. Oh, I didn't. I'm just not reading it carefully. x2 equals 2 plus x3, and therefore x2 is equal to 2 plus 0, or 2. Let me just label this here so we can read it. How about parentheses? That's a bit misleading. Now, I know the value of x2. It's a 2. I know the value of x3. That's a 0. I can plug them in here. 3 plus 2 times x2. Well, x2 is a 2. 2 times 2. Plus 0 times x3. That is, well, x3 is 0 as well. So we have 3 plus 4 is 7. So our solution is x1 equals 7, x2 equals 2, and x3 equals 0. That's called back substitution. The back means this. We're working backwards. We get a solution for our last variable. We leverage that to get the solution for the next to the last, and then we use those to get the solution to the next one back up, and you keep going until you've worked your way back to x1. You could do that here as well, for instance. But in the interest of time, I think I'll leave it alone. Here, this one says, what do we have? x1, x2, x3, x4. x4 equals 4. x3 is 13 minus 3x4. And then you plug the 4 in for x3. Then that gives you x4 and x3. Use those to find x2. Use those to find x1. That's the strategy. Okay, now, something that is, I guess I haven't said it here, but we're all thinking it. Oh my gosh, this is so intensive with arithmetic. Am I going to be stuck doing piles and piles of arithmetic for a whole semester? And the answer is mostly no. There are options we have for options for doing this with technology, and I'm going to show you one of those right now. So what I'm going to do is switch over to Octave. Octave is a free lookalike to MATLAB. MATLAB might well be the, looks like I don't have it started yet. MATLAB might be the premier numerical analysis package that's out there. That means using numerical techniques to solve math problems. And Octave is a freeware lookalike. So now I'm just going to, CLC means clear command. I don't care if you know that or not, but I'm just trying to clean it up. Okay, now I'm going to enter a matrix that is the matrix of the equation we were looking at. So I'm going to give it a name. A equals left bracket, hit return, and now I'm just going to read the top row 1129. I am just copying that first system that we did on the first page of the notes. I'll switch back to that in just a moment. 24 minus 3, 1. And the third row was 3, 6, minus 5, 0. And close up the back bracket, and it shows me the matrix. And that is the matrix that represents, let's pop back there if we can, this system of equations right here. So 1, 1, 2, 9, 9, 1, 0 down the right. That's what we're looking at when we look at this matrix right here. Okay, now wouldn't it be nice if we could just get to the row-reduced echelon form of this matrix with a single command? Well, it turns out we can. And the command is rref, and you press enter, and bang, there it is. We get ones down the diagonal. That's this one, and this one. Zeros everywhere else, and the right-hand side is 1, 2, 3. Now, the formatting is not so nice here, but it's easy to fix. There's a format command, and then you tell it what format you want. Format rat. Rat does not mean rats and mice. It's an abbreviation for rational. So now if I ask again for the row-reduced echelon form of A, I get something that's pretty easy to read. x1 is 1, x2 is 2, x3 is 3. So there's the solution. I have a unique solution. All right, I want to do the other ones that we had on the first two pages very quickly, just to convince you that this is fast. I am looking at the second one, and I'm entering them the way I am. We do have some options, but visually it makes it look like the matrix that you're expecting. So I am, maybe I should show you where I am. I am second page of the notes, looking at that second one, and then I'm going to do this one after that. So take this guy right here. And that first row is 1, 1, 2, 9. 1, 1, 2, 9. Press enter. 2, 4, minus 3, 1. Press enter, and then finally 3, 5. 3, 5, minus 1, and 10. Close up the bracket. There's my matrix. And now if I want to solve that the way I did it before, RREF, I called that matrix B. push the wrong key there. B. So RREFB, there it is. And that rational form actually gives this to me as in fractional form, which is really quite nice. It's the same form that we get by solving this by hand. So if you remember, so let's take a look at this right hand side. For instance, 35 halves minus 17 halves, 0. And if I pop back to my handout, there's the column 35 halves minus 17 halves and 0, only with a whole lot less work, right? So if you know how to read these matrices, it's a really tremendous advantage. And this last one, you could do it exactly the same way. You could enter that and ask for the row reduced echelon form, and you'll find out that it has no solution. Actually, why don't we do that? Because I wasn't sure I had the right number there. So so what I hope you can see, it says C equals and then a square left bracket, and then I type in my matrix 1, 1, 2, 9, next row 2, 4, minus 3, 1, and the last row 4, 6, 1, 1. Close that bracket up, and let's go for the RREF. I call that C, and that's what we should have gotten. Oh, of course, it doesn't really tell me anything, and I'll point out the why it doesn't. This last row, let me check the others. Yes. It appears to be consistent. That number was in question, remember? So I went back and checked it off screen, and it came up with a 52. I think I had a 53 or something there the first time. It was wrong. But no matter what you have, as long as it's not 0, in this case 52, notice if you divided this row through by 52, you'd have 0, 0, 0, 1, right? And that is exactly what we were seeing out of octave. And of course, it's correct. You would get a 1 there. So anyway, you can save yourself a lot of trouble by using a software package like Octave, or if you have access to it, MATLAB is great too. MATLAB is a commercial package for you can buy a student version of it for $100, $99, and it's a great package. I recommend it, but you can get Octave for free. So all you do is type in download GNU, G-N-U, GNU Octave in your browser, and you will find out how to install it for absolutely nothing. It works on both PCs, Macs, and on all of the major versions of Linux. So if I type download Octave, there it is. GNU Octave, that's probably the one I would go to. And it gives you a little information here, and you can download it. So get whatever version you want. By the way, I think most of the major distributions of Linux now have Octave built in, but if not, it's easy to add it to them. Okay, now let me show you how to do that with a calculator, because that is also useful. Okay, I am switching over right now to my calculator, and I'm going to show you how to row reduce this matrix with a calculator. And what we're going to be doing is making use of, I don't know if you can see it on the screen there very well, but right, if I can get it to focus, pretty fuzzy. It says matrix right there. It's over the X inverse button. So What I'm going to do is go to second matrix, and I'm going to enter a matrix. So, whoops, that's not what I wanted. You can see what I got entered in there before. It might be this one, I don't know. Close, but not quite. So second matrix here, and now I have three different menus. I have the names, which you'll see in a moment, math, and edit. Edit's what we want to do right now. Once you select edit, you can change the size. So for instance, if I want this to be a 1 by 2 matrix, that means 1 row and 2 columns. That's okay. And I can put it back to what I want. In this case, I have 4 columns and 3 rows. The rows are always listed first. 3 rows, 4 columns. Press enter, and I'm ready to start entering. So this by default will go in order of rows. So 1 1 2 9, 1 1 2 9. Next row is 2 4 minus 3 1, and 3 6 minus 5 0. And if I quit out of here, actually if I just press matrix again, now I can go for this names, and I'll show you what the names are for. If I highlight row 1, so that will give me matrix A, press 1, it copies its name to the screen. And then if I press enter, whoops, there was a problem. I had some other garbage in here. Let's try again. Second matrix. Is it there? Yes, there it is. So there is the matrix. And if I want the row reduced echelon form, second matrix math, cursor down to RREF, then insert the name, whoops, matrix A. That gives me the RREF of this matrix. We got that with a fair amount of work. And one's down the diagonal, 1, 2, 3 on the right hand side. That's it. Now this also has the REF. So if I go to second matrix math, scroll down here right above RREF, I have the row echelon form. And this will, whoops, wrong menu. This will give it to you. So there it is. And just like with MATLAB, you can get this in fractional form if it's appropriate. So I can go to Math, to Frac, and there it is. There's a row echelon form. By the way, the row echelon form of a matrix is not unique, but the reduced row echelon form is. So this is quite handy. I recommend the calculator, but I recommend also learning how to use Octave or MATLAB, because in more advanced work it is extremely useful, and particularly people want to work as engineers or scientists in the future. You will probably encounter MATLAB, and if you know Octave, you know MATLAB. Okay, that takes care of the first 4 pages. And we are almost done. The reason is we want to talk about homogeneous systems here, and then a little bit of theorem and some geometric insight. But I think after that, what you're going to find in the notes is I don't expect that you would be able to write down all the stuff I was writing in order to make Octave work. So I actually recorded a session. So I think this is one of the homework problems, actually. So I showed you how to solve that using Octave, and that goes on for a couple of pages, and then it gets to the exercises. So we're just about finished here. Let's wrap this up, and then we'll be done.